When I say that the universe may be trying to kill us slowly, I do not mean that it has intentions or plans. The universe is not a character. It is a set of physical laws, fields, and particles playing out over vast scales of space and time. But if I look at those laws honestly and I think about what they imply for life, then the picture is not gentle. It is harsh, indifferent, and on long enough timescales, almost certainly fatal. In this monologue, I want to walk through why that is, using what we know about gravity, dark matter, dark energy, space-time, and cosmic expansion. I want to stay close to the data and the theory and let the implications speak for themselves. Let me start local, with gravity. Gravity is the weakest of the four known fundamental forces, but it dominates on large scales because it is always attractive and it acts on mass and energy, which are everywhere. Gravity is the reason you are held to Earth, the reason Earth orbits the Sun, and the reason the Sun exists as a star. Without gravity, there would be no stars, no planets, no chemistry as we know it. So gravity is the first thing that both creates the conditions for life and threatens it. The Sun is a stable star right now because the inward pull of gravity is balanced by the outward push of pressure from nuclear fusion in its core. That balance is called hydrostatic equilibrium, but it will not last forever. Over billions of years, the Sun converts hydrogen into helium. The composition of the core changes. The fusion rate changes. The luminosity changes. We know from stellar evolution models tested against star clusters and observations of many stars at different stages that the Sun's luminosity has been increasing slowly. In roughly 1 billion years, it will be bright enough that Earth's surface will likely become too hot for liquid water oceans, even before the Sun becomes a red giant. So, at the scale of 1 billion years, our own star, through normal, predictable stellar physics, will likely end surface life as we know it. That is not malice. It is just gravity and nuclear physics doing what they do. We understand this because we can model stars as self-gravitating balls of plasma. We use equations of state, nuclear reaction rates, radiative transfer, and we compare those models to real stars. We see stars of different masses and ages. We see red giants, white dwarfs, main sequence stars. We see the same patterns in many galaxies. That gives us high confidence in the broad picture. So the first slow attempt of the universe to kill us is simply that stars like the Sun are temporary. They are long-lived compared to human timescales, but they are not eternal. If we zoom out beyond our solar system, we see that our galaxy, the Milky Way, is also shaped by gravity. But here, dark matter becomes important. When we measure how stars and gas rotate around the center of the galaxy, we find that the outer parts move faster than they should if only the visible matter were present. If we apply Newtonian gravity or general relativity to the luminous matter alone, the galaxy should not hold together the way it does. The rotation curves are too flat. We see similar discrepancies in many galaxies and in galaxy clusters. The simplest and most successful explanation is that there is additional invisible mass, dark matter. It does not emit, absorb, or reflect light in any significant way, but it gravitates. It makes up about 85% of the matter in the universe, while ordinary matter, like protons and neutrons, is only about 15%. We infer dark matter from gravitational effects, galaxy rotation curves, gravitational lensing, the motions of galaxies and clusters, and the pattern of temperature fluctuations in the cosmic microwave background. Dark matter is not directly trying to kill us either. In fact, without it, galaxies like the Milky Way might not have formed in the way they did. Dark matter clumps under gravity. It forms a cosmic web of filaments and halos. Ordinary gas falls into those dark matter potential wells, cools, and forms stars and galaxies. So dark matter helped create the large-scale structures that made life possible. But dark matter also sets the stage for a universe where gravity can pull matter together into dense regions, stars, black holes, neutron stars, and galaxy clusters. Those dense regions can be dangerous. Supernovae explode. Gamma-ray bursts beam intense radiation. Supermassive black holes at galaxy centers can produce powerful jets. On cosmic timescales, these are common events. Our galaxy is relatively quiet at the moment, but it is not guaranteed to stay that way forever. We know about these violent events from direct observation. We see supernovae in other galaxies. We detect gamma-ray bursts with space telescopes. We observe active galactic nuclei and quasars powered by accretion onto supermassive black holes. We measure their spectra, their light curves, their host galaxies. We can estimate how often such events occur and how powerful they are. In some cases, if a gamma-ray burst or a nearby supernova happened close enough and pointed toward us, it could strip away our ozone layer or flood the surface with ionizing radiation. There is debate about how likely that is on human timescales, but on geological timescales of hundreds of millions of years, such events are not impossible. Again, this is gravity, nuclear physics, and high-energy astrophysics playing out in a universe where matter clusters and collapses. Now, if I zoom out even further, I have to talk about cosmic expansion. In the 1920s, Edwin Hubble and others observed that distant galaxies are receding from us, and that their recession speed is roughly proportional to their distance. This is not because we are at the center of an explosion. It is because space itself is expanding. General relativity, Einstein's theory of gravity, allows spacetime to be dynamic. The geometry of spacetime can stretch. The expansion rate is described by the Hubble parameter, which changes over time. For the first several billion years after the Big Bang, the expansion was slowing down because gravity from matter was pulling things together. But in the late 1990s, two independent teams measured the brightness of distant Type 1a supernovae, which are used as standard candles because they have relatively uniform intrinsic luminosities. They found that those supernovae were dimmer than expected. That implied that the expansion of the universe is not slowing down. It is accelerating. To explain this acceleration, we introduce dark energy. Dark energy is a name for whatever is causing this accelerated expansion. The simplest model is that dark energy is a cosmological constant, a constant energy density filling space associated with the vacuum itself. In that model, dark energy has a constant density per unit volume, even as the universe expands. Its pressure is negative in the sense used in general relativity, and that negative pressure drives accelerated expansion. Observations of the cosmic microwave background, especially from missions like WMAP and Planck, combined with supernova data and large-scale structure surveys, support a universe that is about 5% ordinary matter, 27% dark matter, and 68% dark energy, with the dark energy behaving very much like a cosmological constant. So we live in a universe where, on the largest scales, gravity from matter tries to slow expansion, but dark energy dominates and speeds it up. This has deep consequences for the fate of the universe. In a matter-dominated universe without dark energy, the expansion could either slow and reverse in a big crunch if the density were high enough, or keep expanding forever but decelerate, with structures continuing to form. With dark energy, especially a cosmological constant, the expansion accelerates. Galaxies that are not gravitationally bound to us will recede faster and faster. Over very long time scales, they will cross our cosmic event horizon. Their light will never reach us. The observable universe will effectively shrink to our local gravitationally bound group, the Milky Way and its neighbors, which will eventually merge into one large galaxy. We know this is the likely future because we can measure the current expansion rate, the matter density, and the dark energy density, and we can evolve the equations of general relativity forward in time. There is some uncertainty in the exact value of the Hubble constant today, and there is active debate about small tensions between different measurement methods, but the broad picture is robust. dark energy dominates, and accelerated expansion will continue for a very long time if dark energy remains constant. What does this have to do with the universe killing us slowly? In an accelerating universe, the large-scale structure that we see today becomes more and more isolated. Over tens of billions of years, distant galaxies disappear from view. New star formation declines as gas is used up or locked away in stellar remnants. The universe becomes a quieter place in terms of new luminous structures. On even longer timescales, stars themselves will burn out. Low-mass stars, like red dwarfs, can live for trillions of years, much longer than the current age of the universe, which is about 13.8 billion years. But even they will eventually exhaust their fuel. The universe enters what is sometimes called the degenerate era, dominated by white dwarfs, neutron stars, black holes, and cold planets. The night sky, if any observers remain, will be far darker than ours. The physics behind this is straightforward stellar evolution and thermodynamics. Fusion requires fuel and sufficient temperature and pressure. Once the fuel is gone or the conditions are no longer right, fusion stops. The star cools and fades. We test our models of stellar evolution today by looking at populations of stars in clusters and galaxies, and by comparing their colors and brightnesses to theoretical isochrones. Those tests give us confidence to extrapolate forward, even though no one has seen a trillion-year-old star. The equations do not suddenly change. As time goes on, gravitational interactions between stellar remnants and planets will gradually rearrange systems. Some objects will be ejected into intergalactic space. Some will fall into black holes. Over extremely long timescales, even stable-looking systems are not perfectly stable. Gravity, again, is slowly changing the configuration of matter. In a universe with dark energy, the background spacetime is expanding exponentially on the largest scales, but local bound systems remain bound. The expansion of space does not tear apart atoms or solar systems. It acts between structures that are not gravitationally bound. So your body is not expanding with the universe, but your cosmic neighborhood is drifting away from others. Now, there is an even more extreme possibility that dark energy is not constant. We usually describe dark energy using an equation of state parameter, W, which is the ratio of its pressure to its energy density. For a cosmological constant, W equals -1 exactly. Observations so far are consistent with W being very close to -1, maybe exactly -1, but with some uncertainty. If W is less than -1, we call that phantom energy. In such models, the energy density of dark energy actually increases as the universe expands. That leads to a scenario sometimes called the Big Rip. In a Big Rip, the expansion accelerates so violently that in finite time, not only do galaxies move apart, but eventually even galaxy clusters, galaxies, solar systems, and finally atoms are torn apart by the expansion. The timescale for that, if it were real, depends on how far below -1 W is. Current data do not strongly support W -1, and many theorists are suspicious of phantom models because they can violate energy conditions in general relativity and cause instabilities in quantum field theory. But the point is that our knowledge of dark energy is incomplete. We know it drives accelerated expansion. We know its density today. We know it behaves very much like a cosmological constant, but we do not know its fundamental nature, and we do not know for sure how it will behave in the far future. If dark energy is a true cosmological constant, the universe heads toward a de Sitter phase, an exponentially expanding spacetime with a constant vacuum energy density. In that case, the long-term fate is often called heat death, or the Big Freeze. As stars burn out, as matter falls into black holes, as black holes themselves evaporate via Hawking radiation over timescales of about 1064 to 10100 years, depending on their mass, the universe becomes more and more dilute and cold. The temperature approaches a tiny value above absolute zero, set by the de Sitter horizon. Entropy increases. Free energy, the kind of energy that can do useful work like powering life or machines, becomes scarce. At some point, there is effectively no more structure forming, no more chemistry as we know it, just a thin bath of low-energy photons and extremely diffuse particles in an ever-expanding space. Life, as far as we understand it, depends on energy gradients, differences in temperature, chemical potential, or radiation intensity. In a heat death scenario, those gradients fade away. The universe does not actively destroy life, but it removes the conditions that allow life to persist. We arrive at this picture by combining general relativity, thermodynamics, quantum field theory, and observational cosmology. Hawking radiation is derived by considering quantum fields near a black hole event horizon in curved spacetime. The idea that entropy increases and that systems tend toward equilibrium is deeply rooted in statistical mechanics. The cosmic microwave background gives us a snapshot of the early universe when it was about 380,000 years old. And its tiny temperature fluctuations tell us about the initial conditions for structure formation. Large-scale galaxy surveys map how those structures have grown. When we evolve the equations forward, we see that with dark energy, structure growth slows and eventually stops on large scales. The universe becomes dominated by the smooth dark energy component. There is another layer to this. The vacuum itself may not be completely stable. In the standard model of particle physics, if we extrapolate the measured masses of the Higgs boson and the top quark, the Higgs potential may be metastable. That means our current vacuum state might not be the absolute lowest energy state possible. There could be a deeper vacuum, a true vacuum, separated from our current state by an energy barrier. Quantum mechanics allows tunneling through barriers. So in principle, a bubble of true vacuum could nucleate somewhere and expand at nearly the speed of light, converting our region of space to this new vacuum state. Inside that bubble, the laws of physics could be very different. Particles could have different masses, forces could have different strengths, chemistry as we know it could be impossible. This is called vacuum decay. If it happens, we would have no warning, because the bubble wall would reach us at light speed. However, the calculated lifetime of our metastable vacuum, given current measurements, is much longer than the current age of the universe by many orders of magnitude. The uncertainty in the top quark mass and in high-energy physics beyond the standard model also leaves room for the vacuum to be stable. So this is a serious theoretical possibility, but not an imminent concern on any practical timescale. What connects all these ideas is that the same laws that allow a universe with structure, stars, and life also predict that those conditions are temporary. Gravity forms stars, but then stars evolve and die. Gravity forms galaxies, but dark energy eventually isolates them. Quantum fields allow particles and forces, but they might also allow vacuum decay. Thermodynamics allows complex structures to form out of lower entropy initial conditions, but it also drives the system toward higher entropy over time. The arrow of time, as we experience it, is tied to entropy increase. On small scales and short times, local order can increase, like when a star forms or when life evolves. But globally, the entropy budget is moving in one direction. From the point of view of life, especially intelligent life, this looks like a slow process of being squeezed out by the large-scale evolution of the universe. There is no single catastrophe built into the standard cosmological model. Instead, there is a sequence of transitions: the end of star formation, the fading of starlight, the evaporation of black holes, the approach to thermal equilibrium. On top of that, there are local risks: asteroid impacts, nearby supernova, gamma-ray bursts, stellar evolution, and the internal dynamics of galaxies. The universe is not safe, and it is not static. It is important to be clear about what we know and what we do not know. We know that the universe is expanding and that the expansion is accelerating. That is based on multiple independent lines of evidence: supernovae, the cosmic microwave background, baryon acoustic oscillations, and galaxy clustering. We know that most of the matter is dark, based on gravitational effects. We know that gravity is well described by general relativity on many scales, from the precession of Mercury's orbit to the bending of light by galaxies, to the detection of gravitational waves from merging black holes and neutron stars. We know that stars form, evolve, and die in ways consistent with nuclear physics and observations. We know that entropy increases in closed systems, and that the universe, as far as we can tell, had a much lower entropy in the past than it does now. We do not know what dark matter is made of. It could be a new kind of particle, like a weakly interacting massive particle, an axion, or something more exotic. It might involve modifications to gravity on certain scales, though pure modified gravity models have trouble matching all the data as well as particle dark matter does. We do not know what dark energy is at a fundamental level. It could be a cosmological constant, or it could be a dynamic field, like quintessence. We do not know if dark energy will stay constant forever. We do not know if the vacuum is truly stable. We do not know if our understanding of physics remains valid all the way to the incredibly long timescales involved in black hole evaporation and heat death. Quantum gravity, the theory that would unify general relativity and quantum mechanics, is still incomplete. There might be new physics that changes the far future picture, just as dark energy changed our view of cosmic fate compared to what we thought before the 1990s. Even with those uncertainties, the trend is clear. On human timescales, our main threats are local: our own star, our own planet's geology and climate, nearby astrophysical events. On cosmic timescales, the entire environment that allows complex chemistry and biology appears to be temporary. The universe is expanding, cooling, and in a sense, running down in terms of free energy. The phrase "the universe may be trying to kill us slowly" is a way to capture that tension. The same physics that gives rise to life also sets a clock on how long conditions remain favorable. There is a subtle point here about observation and selection. We observe the universe at a time when stars are still forming, when galaxies are still bright, when the cosmic microwave background is still detectable, and when dark energy has only recently become dominant. Some cosmologists think about this in terms of anthropic reasoning. We could only find ourselves in a universe, and at a time when the conditions allow observers to exist. That does not explain the physics, but it reminds us that our vantage point is not random. We live in a cosmic window, where the universe is old enough to have formed heavy elements and planets, but not yet so old that star formation has ended. This window is long in human terms, but short compared to the full future evolution of the cosmos. As I look at all of this, I do not see a universe that is friendly or hostile. I see a universe that follows mathematical laws that we can, to a surprising extent, write down and test. Those laws imply that structure emerges from initial conditions, evolves, and then fades. They imply that spacetime itself is dynamic. They imply that most of what exists is invisible to our eyes: dark matter, dark energy, and quantum fields in the vacuum. They imply that, in the long run, the universe is not a stable home for life. Life is a transient phenomenon in a changing cosmos. The scientific challenge is to refine this picture. We want to measure dark energy's properties more precisely. We want to detect dark matter particles, directly or indirectly. We want to test general relativity on more scales, and look for any deviations that might hint at new physics. We want to understand the early universe better, including inflation or whatever mechanism seeded the initial fluctuations. We want to know how robust our predictions of the far future are, given the unknowns in quantum gravity and high-energy physics. So I end with an open question that sits at the heart of this topic. Is dark energy truly a constant property of spacetime, fixed forever? Or is it the sign of a deeper field or mechanism that will change in the future and alter the fate of the universe in ways we cannot yet predict?